In this video, we're going to talk about chemistry that happens next door to the aldehyde or ketone. We call this position the alpha position. So by the end of this video, you should be able to say that you can draw a mechanism for the tautomerization of an aldehyde or ketone. You can predict the approximate position of a ketoenol equilibrium. You can explain why alpha stereocenters can be racemized and why alpha hydrogens are exchangeable. And you can draw a mechanism for alpha halogenation under acidic conditions. To understand the acidity of the alpha hydrogen, we need to look at the resonance structure of the conjugate base. So first, let's do a deprotonation of our model aldehyde here, or model ketone acetone. So I'm just using a B with a minus to represent some base. So if we do this deprotonation, we're going to get to a species called an enolate. And you'll note that this anion is next door to a carbonyl, so we can actually draw a resonance structure for this. The two resonance forms are the C enolate, where the negative charge is centered on the carbon, and the O enolate, where the negative charge is centered on the oxygen. The O enolate is typically the more dominant resonance structure because oxygen is an electronegative element and therefore better at stabilizing a negative charge than carbon is. And that's actually part of what makes the alpha proton here so much more acidic than a typical alkane. In a non-symmetrical ketone, like the ones in the bottom of this slide, you can actually have two different enolates possible, and often one is more stable than the other, and so you get a more stable one called a thermodynamic enolate, and the one that forms faster, which is called the kinetic enolate. So the carbon that has more hydrogens is going to be the kinetically favored carbon, and the carbon that has more substituents is going to be the thermodynamically favored, unless one of those substituents is destabilizing, but that's getting a bit complicated. A couple of things to note about the thermodynamic enolate. The thermodynamic enolate is going to be the more stable enolate. You can think about the stability of the olefin, so you should be familiar with that from Orgo 1. And then this species is going to be more dominant when a weaker base is used. And that's called soft enolization. In the next example, we can see that there's 3 hydrogens on one side and 2 on the other. These happen to be next to an aromatic ring, and so these are called benzylic hydrogens. This is the benzylic position right next door to a phenyl group. And those are more acidic because if you deprotonate one of these hydrogens, that anion would be stabilized by resonance forms through this ring. They're especially acidic when they're next door to a carbonyl because now that anion can be stabilized not only through the aromatic ring but also onto the oxygen. So that gives us this structure here, which again is going to be our thermodynamic enolate, and then the other one we just call the kinetic enolate. So overall, the acidity of the alpha hydrogen can be explained by resonance effects. There is also a significant inductive withdrawing effect of the carbonyl that's caused by the presence of the dipole moment, which is very strong for a carbonyl. And that's going to result in a significant positive charge at this position. That's going to also be withdrawing electron density from this carbon, making this carbon easier to deprotonate. So when we start talking about equilibria between the ketone and the enol form, we need to think about what the pKa values for these carbonyl compounds and the conjugate acid of the base. So for an equilibrium to occur, the pKa of the carbonyl compound on the one side and the pKa of the conjugate acid of the base on the other should be less than 10 units apart. And if they're like 9 units, then you're going to still have almost all enolate. So you typically need a gap that's closer to 5 to get any kind of real equilibrium. we'll take a look at the general mechanism here. So we form the enolate, and then we also form a protonated base. So this is the conjugate acid of the base that I had been mentioning. And now we take our lone pair and we protonate. To form the enol. So we can use pKa values to predict which side of the equilibrium is going to be favored. The simplest way to do that is to write the pKa of the acid or conjugate acid on each side. So whichever acid has the higher pKa is going to be the species that wants to keep the proton the most, and so the equilibrium will favor that side. So in this case, acetophenone is going to be the favored side of the equilibrium, so more of the mixture is going to be as the acetophenone than as this enolate. So to summarize that, we would say the equilibrium lies to the left. So when you have a problem where you need to predict which direction the equilibrium lies, and you have an acid-base reaction, then just put down the pKa's and then it'll favor the higher number. So now we're going to talk about acid catalyzed tautomerization. So in the case of acid catalyzed tautomerization, we start by activating our carbonyl, and then we use water to deprotonate, and we're going to push those electrons all the way up to the oxygen, because oxygen is going to be better at holding those electrons, and because we don't want any carbons with 5 bonds. And that gives us, again, our enol. Conversely, if we're starting with the enol, we would protonate. Then deprotonate the oxygen. And that would give us our ketone and regenerate the catalyst. This tendency to convert between keto and enol forms also leads to a tendency for alpha positions to undergo racemization. Racemization just means converting from a single enantiomer to a racemate, which is an equal mixture of 2 enantiomers. So under either acidic or basic conditions, the alpha proton here can be deprotonated, proceed through the enol or enolate, and then reprotonation will not be selective. So we'll go ahead and draw that out. We're going to deprotonate to form the enolate. Now we see that our stereocenter has been destroyed. And protonation can happen either from above or below the pi bond. And so there's nothing to actually control which one of those happens, and you'll get an equal mixture. So we reform our pi bond, and we deprotonate our conjugate acid, and that gives us the carbonyl, but we have both enantiomers here. This can also proceed through the acid catalyzed mechanism. And again, when we reprotonate, we do not have any control of the stereochemical outcome. And we again get the racemic mixture. That's what this symbol here means. So finally, we're going to close out with a cool new reaction that just combines keto-enol tautomerization with the bromination of the resulting pi bond, and then you reform the carbonyl and open bromonium. Snicker snack. So let's draw it out. So first thing, check the reaction conditions. We see that we have the ketone and we have acid. So we can go ahead and activate our carbonyl. Next, we're going to deprotonate. And then we're going to react with bromine just like we would if we had a normal olefin. So our pi bond is going to attack, kicking out bromide, and then the lone pair on bromine can come back in and prevent us from actually forming a positive charge there. And the resulting intermediate has this bromonium ion. And we have our alcohol there. That's going to immediately reform the carbonyl and open the bromonium to give you the product alpha bromoketone. So again, we do an acid catalyzed ketoenol tautomerization by protonating and then deprotonating the alpha position, and then we react that pi bond with Br2 just like we did in Orgo 1, but now we can kick down this lone pair to reform the carbonyl and open up to form the bromonium. Sorry if you're hearing Claire. And then finally, we're going to deprotonate that. We'll just use a general base here.